Assalamu alaikum wa rahmatullahi wa barakatuh. Bismillah ar-Rahman ar-Rahim. So this is the third lecture on visualization. Okay, so we covered so far three types of plots, right? Line plots, scatter plot, and bar chart, right? And the last one is histograms, and I hope that inshallah today we will cover it in full. We started to introduce that last time, towards the end of the lecture. We talked about numerical distributions. So bar charts are used for categorical distributions, right? When I have a categorical variable that has individual specific values, then I can see the distribution of that variable using a bar chart, okay? But for numerical variables, it doesn't make any sense to plot individual values of this numerical value, especially if it's a real number, for example. Even if it's integer, the range might be huge. It doesn't make sense to see the counts for every individual value. So what we do is to do what we call binning, which is having bins or ranges or intervals. Okay, so we count the number of individuals within each interval or within each bin, and then we look at the distribution. Okay, and that's what we will see inshallah today. So the first step in drawing a histogram is to do the binning of the values of the numerical variable. So binning is defined as counting the number of numerical values that lie within ranges. So within each bin is defined as a range. So the bin has the count for the elements or the individuals that are belonging to that range. The bin is defined, each bin is defined with, as we said, as a range. So the range has a lower bound and an upper bound. So as usual, the lower bound is inclusive and the upper bound is exclusive. Okay, and we use this notation to indicate the inclusion of 185 here and the exclusion of 190. So every value that is greater than or equal to 185 and less than 190 will belong to this bin. Okay, so that's how we define bins. We define it with the lower bound and upper bound, and the lower bound is included, the upper bound is excluded. Okay, so if I have this series of values, 188, 170, and so on, then 188 will belong to this bin. Okay, how about 170? Which bin it will belong to? This one? Then this one. Okay, remember that it's inclusive for the upper limit and exclusive for the inclusive for the lower limit and exclusive for the upper limit. So 170 will belong to this one, not this one. Okay, is that clear? And so on. 185, 189 will belong here, 163, 183, and so on. Okay? So the last one, 173, should be here. Okay? So this is what we call binning. We map each value into one bin. Can one value belong to multiple bins? No. By definition, the bins should not be overlapping. Okay, so one value should belong only to one bin. Okay, now let's go through some examples of binning. Okay, so we start with, I think this data we saw it before, which is the top 200 movies. Okay, for each top 200 movies at 2017. Each movie has the title, the producer, the income, the adjusted income, and the year of production. We'll just add one new variable here, which is the age, okay, which is how old the movie is. So to do that, we will subtract it from 2020 and add that as a column. So the top movies now will have a new column, which is the age. And we will only focus on the age in this exercise, actually in the whole lecture probably. Okay, before we do binning, it's good to know the entire range, okay, of the values. So now we want to see the distribution of years of the top 200 movies. Okay, so before doing that, before drawing a histogram, it's good to know the range that we are looking at. So the minimum and the maximum here is 3 and 99. Okay, so here's an example of bins. So bins are defined as an array. So we have here 0, 5, 10, 15, and so on. So what's the meaning of this? That means that the first bin, the bounds of the first bin is 0 to 5. And the second one is 5 to 10. And the third one is 10 to 15, and so on. Okay, so which means that each number here is the lower bound of the current bin and also the upper bound of the previous bin. Okay, is that clear? So how many bins we have here? From 0 to 5, 5 to 10, 10 to 15, that's 3, 4, 5, 6, 7, okay? And 100 here doesn't define a new bin, it just defines the upper bound of the last one, okay? So the last number here is not 100 or more. By definition here, this last number is just defining the upper bound of the last bin. So it's not a new bin. So the number of bins here is 7. Okay? Now let's use the method bin for a table that will give us the count for each bin. Okay, so you would expect that we have 7 bins, right? Okay, so now if we call the method bin for the table, we indicate that we want to bin over the age column. That's what we want to count the values for, and given those bins. Okay, so it takes two parameters in this case, the column where we want to get the distribution for, and the definition of the bins. Okay? Yes. Question? Yes. Okay, what do we mean by a bin? Dalal, right? Who's the Hadil? Sorry, Hadil.
Interval range.
Yes, it's an interval. Okay, it has an upper bound, a lower bound, and upper bound. So 0 to 5 here is a bin. Okay, and 5 to 10 is a bin, and so on. No, from 0 to 5 is one bin. From 5 to 10 is a second bin, and so on. Okay, so here is the data that we get out of calling the bin function. So what do we get from that? So how many elements in the first bin? 12. So these are the elements that are of age. These are the movies. That's the number of movies that are of age 0 to 5, but less than 5, right? So 0 or more, so 0 or greater to less than 5. Okay, and the second one is 5 or more up to 10 exclusive, and so on. You notice that the last line here is 100, although that we said that it's not a bin, right? But it is included in the bin table, but it will always have 0 count. Okay, it will always have it will always have 0 count because it's not actually a bin. It's just 100 here is just to indicate that this bin goes from 65 to 100.
Age count. Automatically with bin function.
The age, yes, exactly. Yes. Okay. So bin data is a table that was generated from the bin function. The bin function takes the column and it will generate a new column, which is the count for each bin. Okay. Are you following with me so far? Okay. Now, if I get the sum of the counts, what should it be? The sum. The number of movies, which is, if you noticed, 200. Okay, so that's the number of movies, right? Because we said that the bins are mutually exclusive, right? There's no overlap. So the total counts over the entire bins is just the total population, okay, which is the total number of movies. Now, here's another example of binning. So what are the bins here? 0. How many bins we have here? Huh?
2.
Only 2?
7.
7. Okay, from 2 to 7. That's a big jump.
From 0 to 100, right?
So what do we mean by a range 0, 125?
By each 25 step.
Yes, with step 25, right? So from 0 to 25, that's the first bin. 25 to 50. 50 to 75. 75 to 100.
4.
Then we can, so we'll not go beyond that because the upper limit is 101 here. Okay, so we will have 4 bins, right? So that will give us 4 bins. Why do we have 5 rows then?
The last one.
Yeah, because the last one is just the upper limit of the last one.
The last one is 100, not 101.
Good question. Why do we have 100, not 101?
25 step. The range.
Because that's how the A range function runs, right? It adds 25, the step 25, until you get beyond that number, and that number is not included. Even if we put here 125, it won't be included, right?
But it will be 125.
It will, no. Okay, so A range will give us an array. Okay, the array in this case will be 0. If this is 125, it will be
125.
no. It will stop at 100 because always the upper limit is excluded. Okay, remember the upper limit always is excluded. If it was 126, then it will include 125. Okay, revise the one of the previous lectures. Yes.
99. It will drop the last.
If it's 100,
99. Oh, yeah, 100.
yeah. If it's 99, it will drop, of course, 99. But if it's 100,
It will drop the last bin.
it will drop the last bin. It will be 3 bins only. Okay, that's similar to 125. Anyway, okay. So you know now, you understand this now, right? Okay. Here's another one. How many bins we have here?
2.
2. Any other answer? 2? What are the 2, Serene? What are the 2? And 25 to? No, 25 to 50, because A range is going by step 25. Okay, so 0, 25, and 25 to 60, to 50, sorry, to 50. Okay? So 88 movies within this age and 70 within that range. Okay? Now you will see that we have 0 here. We said that that's by default, even though we might have some movies that have age of 50 here. Okay? So if we want to check that, we'll see that we have 4 movies of age 50, but as we said, that's not a new bin, it's just the upper bound of the last one. Okay? Any question about binning? Good. Now we get back to the slides and we continue in the way of how histograms will be drawn. So we said the first concept is binning. We count for each bin the number of individuals in each bin. Now the second one is the area principle. So look at this picture and read the text below and tell me what's going wrong here. What's wrong? Nothing wrong?
It's not the bin on the size. The actual size.
So it says that this new one is 70% bigger than this one. Right? Like, what's wrong with that? This is bigger, right?
But maybe the size, maybe in the appearance of the
Okay, so the figure doesn't show that it is just 70%. It's much bigger than 70%, right? That's much bigger. Okay, so the area here is not to scale. The area here is not to scale, and that's what's wrong in that figure. Okay, so the area principle says that areas should be proportional to the values they represent. So if I said that this is double, then the area means double. It should be double. It's not more, it's not less. Okay? To have the same meaning. So for example, if you represent 20% of a population by this triangle, then this should be 40%. Not this. Okay, because that might not be double the area. Okay, so that's the simple area principle, and it's intuitive, of course. It's clear. Now we will use these two concepts, binning and the area principle, to draw histograms. So in drawing histograms, of course, as we said earlier, histograms represent the distribution of numerical variables, not categorical. Okay, categorical, if we need to look at the distribution of categorical variable, then we should use bar charts. Okay, but histograms are for distributions of numerical variables. We will use bins, which means that there will be one bar. It will look like, you will see it very soon, it looks like a bar chart, but actually it's not. Okay, it has a one bar for each bin. Remember, in bar charts, we have one bar also, but per value, per category. Okay, because it was for categorical values, right? Variables, right? Here, we have one bar for each bin. Okay? The other principle, which is the area principle, will indicate that the area of each bar, is the percent of individuals in the corresponding bin. Okay, we will see that very soon in an example. Okay, but it's not the length. Remember, in the bar chart, the length of the bar indicates the value, right? Here, it's not the length. The area of each bar indicates the percentage of the population. Okay, let's see a demo, and that should be clear by the demo. We are back to the same bins and the same also movies data. So here is the binning table that we had before. Okay, look at this and tell me what we are doing here. Okay, so we are adding a column, which is, it will be called percent. And what are the values in the column? It's the age count divided by 200 and multiplied by 100. What does that mean? A percentage, right? Because it's called percent, right? Okay, so it's the percentage of the population within that bin. Okay, so doing that, we will get a new column which is called percent. Okay, so the percent here is the percentage of the individuals relative to the entire population. So what does that mean for the first bin? 6%. So 6% of the 200 movies, of the top 200 movies, are in the age from 0 to 5, are very recent. Okay? And so on. Now let's try, before we see the histogram, let's try a bar chart. Okay, and see how the bar chart will look like, and then we'll see how the histogram will look like. So from that data, we can plot a bar chart with the x-axis will be the bin, and the y-axis will be the percent. Now, when we say the x-axis is the bin, is it numerical or categorical? Okay, the bar chart by default, the first argument is categorical, right? So it will deal with the bins here, the values of the bins here, as categorical, as labels, as names. Okay, because that's how bar chart works. Okay, and how about the y-axis? It will be just the percent, the values that we just calculated. Okay, remember the bar chart, usually we use it to draw counts, but it can also be used to draw values. Okay, if we have values, it's not counts, it's just values, which the counts are also values, but it's a special value. So here the percentage, and let's see how it will look like. So that's a bar chart for the bins. Okay, So here's the first bin. It has the name 0. It doesn't know that it is from 0 to 5. Okay? It has just the name 0. Here's the name 10, and here's the name 25, and probably these are extruded just to be nicely drawn, so that the names probably will not be overlapping. Okay, how about the y-axis? That's the values that we just computed, right? The first one is 6 here, right? And so on. Even here, it should be 100, by the way, but it is 0. That's why there is nothing here. Okay, it doesn't know that this is a bin. It's just a value. It's one of the values of the table. Okay, and notice here, what is the width of each bar? It's the same. It's equal, because that's how bar chart is plotted, right? Has equal width. Each bar has the same width. Okay. Okay. This is not a histogram. Let's see how the histogram will look like. To plot a histogram, we don't need to do these calculations. We just call the histogram method on the original table, given the bins. So we don't need to call the bin function again. Histogram will do the binning by default, given that given the bins array. Okay, remember the bins array that we had? This one. This one, right? These are the bins that we are talking about. Okay, so now we use the method hist, which will plot the histogram for us. The first argument is the column that we want to look at its distribution, and these are the bins. And forget about this unit for now. Okay, let's look at the histogram. Here's the histogram. Does it look familiar? It looks like a bar chart, right? But it's not exactly. Okay, let's look carefully at this plot. First, look at the x-axis. Look at the x-axis. What do you notice on the x-axis, and compare it with what we have here? So the width of the bars is not equal. So what is the width of the bar here? Yes, that's the size of the bin. That's the size of the range, right? So this bin, remember, it goes from 0 to 5, right? Yes. Okay, so the length, the size, the width of it is just 5. The next one is also 5, 5 to 10, 10 to 15, and then 15 to 25, right? Are you following with me? Okay, and then this one is 25 to 40, and then this one 42 to 65. Okay, and so on. So the width of each bin here depends or indicates the size of the bin. The size of the bin. Okay, that's the first thing. The second thing, is that numerical or categorical? Yes, it's numerical, which means that the numbers here are to scale. Okay, so the difference between 0 and 5, if you look at the difference between 0 and 5, and the difference between 20 and 40 and 60, for example, or 20 to 40, you will see that this is 4 times the other one. Okay, so the values here are plotted to scale. Okay, so it has the numeric meaning. Okay, but in the bar chart, we don't care about that. We look at these as just names. Okay, if you look at the bar chart here, you see this is 0, this is 10, and then this is same distance here is between 10 to 25, because it doesn't actually use these as numbers. It uses these as just names. Okay, but for a histogram, this is a numerical variable. So the x-axis is to scale. You have a question? Go ahead.
For the size, like
the width.
Yes.
Okay.
So like it must be equal or
no, it's not equal. You see here, it depends on how we define the bins. Remember, this is what we define the bins.
But we defined it as one value, like 25 or...
But we said that these numbers indicate, each number indicates the lower bound for this bin, and the upper bound for the previous one. So when we say 0, 5, 10, that means that we have two bins, from 0 to 5 and from 5 to 10. Okay, so that's the first two bins here. Did I answer your question?
Yeah.
Okay. Any other questions so far? We didn't finish the explanation of this graph yet. But it's very important to understand these things. Okay, so the x-axis is numeric, so everything is to scale, just a scale. Okay, so for example, we don't exclude any bin here, even if it's empty. Okay, even if it's not there, all the numbers are represented here. Okay, because the bins are continuous. And as you saw, the width of the bins depend on how we define them, and it can be unequal. Okay, so the x-axis is done. Now let's look at y-axis. Okay, so what is y? What is the length of the bar? So we talked about the width of the bar. We said that the width of the bar is the bin size. That's the range. Okay. How about the y-axis? What is the y-axis? What is the height of the bar here? What does it represent? Now, let's think about percentage. Maybe it represents percentage of the individuals within each bin. Okay, so let's see. Okay, so let's look at this bin, for example. I will just remove this for now. Okay, just to look at the numbers here and the plot. Let's look at this bin. Okay, let's look at this bin. What is the percentage of the population here? First, this is not the count, right? It cannot be the count because the count here is 9, and we have something like maybe 1.8 or so. Okay, so that's not the count for sure. Type. Maybe it's the percentage. Okay, the percentage is what for this bin? It's 9 over 200, which is 4.5 actually. It's not 1.8. Okay, so what's going on here? What do we have here? It turned out that what we plot on the y-axis is the percentage of the population in the bin, but per unit. Okay, per unit within the bin. Okay, so you will see how it is calculated in detail, but this is the meaning of it. So first, let's think about the percentage. We all know the percentage of the population within each bin, right? How it is calculated? It's the count of the population, count of the individuals within this bin over the sum. Okay, so if we plotting here the percentage, it should be 9 over 200 for this bin. I'm talking about this bin, for example. Okay, but what we plot here is that percentage, but per unit. So what is the unit here? This bin is from 5 to 10, right? So it has 5 years, right? So this bin is over 5 years, right? What we plot on the y-axis is the percentage per year. Per year. So to get this number, what should we do? We divide the percentage by 5 to get the percentage per year. Okay? So the percentage per year here is 4.5, right? Or point. So that's 9. Okay, so we were talking about 5 to 10 actually. So that's 9, right? 9 over 5 is 1.8. Okay, so 1.8 is the percent per year here. Okay, so that's actually the percentage. Okay, we did a mistake earlier. Okay, so the percentage is not 9 over 200. That's actually the percentage that we counted before. So the percentage is 9. Okay, over 5 is 1.8. Type. What does it mean to have this to have the height of this is 1.8. That means that in the age of from 5 to 10, the movies among the top 200 movies, okay, there are 1.8 per year movies within that range that appear in the top list. So it's like almost two from the last 5 years. Almost every year we get 2% of the entire population within the top 200. Okay? So that's the meaning of it. So again, the width of the bar is the bin size, and the height of the bar is the percentage per unit. Type, let's think again about this percentage per unit. Okay? What does it mean? It indicates how crowded the bin is. Okay? Which we call it the density of the bin. Okay? If that bin, for example, let me give you that example. Let's say that this bin has so many movies. Maybe 70 movies. Okay? 70 movies within 5 years, that's very crowded, right? So the density is 70 over 5, which will be very high. Okay? Now, look at this bin. For example, this bin is too wide, right? That's from 65 to 100. Okay? It has, by the way, the same percentage like the bin that we looked at before. But how about the density? If we have here 9% of the 200 movies, and we have here the 9%, also 9% of the 200 movies, why do we have this very tall and that's very small, very short? Because the density, the crowdedness for this one is very high, right? Because we divide 9 by 5. But here it is very low because we divide by not 65. We divide by the width of that bin, which is 35. 100 minus 65. Okay, so that's not very crowded, although it has the same number, same count. Percentage is related to count, right? So it has the same count of the individuals, of the movies, okay, but over much larger span of years. Okay, so it's not very crowded. That's why the height of the bar here is short. Okay, do you understand now what is the meaning of the width of each bar and the height of each bar? Okay, so the width is the size of the bin. The height is the density. Okay, is the density, which is the percent per unit. Yes.
You can say also percent per bin.
No, it's not percent per bin. If you look at here, what is it? What does it call? It's percent per year, because the unit of each bin is year, right? Each bin has 5 years, 35 years, 10 years, and so on. So when we divide by the number of years, then the unit becomes per year. Okay, so that means that, for example, in this bin, let's say that this is exactly 1. That means that in that bin, the movies from 40 to 65, we have 1% every year in that top list. 1% here is 2, right? Because we have 200 movies. So it's like two movies every year from that in that range in the top 200 movies. Okay. If you didn't get 100% full understanding of this, you will get it by more details. We will get to the details soon, but this is the idea. Okay, the length, the width of the bar is the bin size. The height of the bar is the density. Now, what is the area? So the area is the width times the height, right? If we do that, then we will get back the percentage. Okay, so the area of the bar here indicates the percentage of the population that belong to that bin. Right? Okay, we'll see the computations very soon. But if you remember, the height, we got the height by dividing the percentage over the width, right? Now, percentage over the width times the width again, because that's the height times the width, it's the area. Okay, so we get the percentage. So the area here indicates the percentage population within that bin. Okay, now that means that, let's say that instead of 100 here, I put 200. Not 200, 500. Just not to be confused with the total population. Let's say that I put the upper bound here to be 500. What will change here in that chart? All of these bins will not change, right? So this one should change or not? How? Will it be shorter or taller? Shorter, right? Because the area will be the same. You remember that the maximum here is 99. So adding more will not add more population. So the same population, same percentage. But what happens is that the width of the bin will increase, which means that the height will decrease. Okay, because the area is the same. Remember, the area of each bar is the percentage. The percentage didn't change in this case, so what will change is just the height. So you will see that this bar, instead of being maybe 0.25, it will be maybe 0.1, but it will be much wider, okay, but it's very short. Okay, now let's get into more details. Before that, let me show you what happens if we changed one of the arguments in the histogram. So now, did you understand why we put unit equal year here? Because that's what we want to see here and what we want to see here on the x-axis and the y-axis. Okay. Now, if we added one more argument called normed, which in short version of normalized. Okay, so normalized equal false. And let's see what will happen, and that will give us an idea of the meaning of that argument. So this one is exactly like the previous command, except that we added false to normalized. So that means that these values are not normalized, and in this case, these values will be just the count. Okay, so now the y-axis is just the count of each bin. It's not even percentage, and of course it's not density. Remember here it was density, right? Percent per unit is density, is how crowded the bin is. Here is just count. Type. What does that mean? That means that this is not a histogram. This is no longer a histogram. Okay? Because in histogram, the percentage, the area indicates the percentage. But here the area doesn't indicate the percentage. What indicates the percentage here? In this plot? Huh? The count, which is the height. Exactly. Okay? Of course, count and percentages are related, right? We just divide by the number of the total population. Okay? But here, the height is indicating the percentage. So that's not histogram. In histogram, the area indicates the percentage, not the height. Okay, in histogram, the area, which is the width times the height, is the percentage. Okay, which means that the height will be the density. Here we don't have the density. And the area here, just 1 second, the area here doesn't indicate anything. Okay, now in this plot, if we change the bin of 100 to 500, what will happen? The height will change? No, because the count is the same. Just the width will increase. That means that shows you that area here has no meaning. Okay? The area here has no meaning. Although that we plotted this by the histogram function, but that's not a histogram. Okay, that's just to show you if we didn't normalize, what will happen. By default, it is normalized, and by default, we will get a histogram, but this is not a histogram. Yes?
If we remove the unit or norm?
If we what?
It's in that unit or norm.
Yes. This is, look at this, Marwa. Look at this. Forget about the unit is just a label. The unit here is just to put here, the word here, and the word here. It doesn't change any values. Okay? So forget about the unit. But here we didn't put the normed, which means that the default value of it is 2, which is to show a histogram. Okay, that's a good question. Is that a bar chart? I heard yes and no. Okay, who said yes? Who said no? Why not?
Not categorical.
Not categorical. Okay, it's not only not categorical because we saw that even if it's numeric, the values will be like labels. But there is something completely different here. Huh?
The bar chart will not change for the ranges. Like the ranges here is.
Yes. So what I think what you want to say there is that the width of the bins here is different, which is not the case in bar chart. In bar chart, always the width is the same because there is no meaning of the width in bar chart, right? Remember that the category in the bar chart is just a name. It's not a bin. It's not a range. Okay. So this is different from bar chart in the y-axis. How about the x-axis? How about the y-axis?
The same.
It's the same. It's the same because if we are just plotting the count, it will be the same height. Okay? But so this is not a bar chart and this is not a histogram. Something in between. Okay? Here's an example when we change the bins. So look at this and tell me how many bins we will get. 10, right? 0, 10, 20 until 100, but of course 100 is not a new bin. So we'll have 10 bins here. So we will get something like this. Is that a histogram or not? Is that a histogram? So in histogram, can we have equal bins? Of course we can, right? We can do anything. We can define the bins as we wish. Okay? So in terms of equal width, that's fine. A histogram can, of course, do equal size bin. It can generally do any width. Okay? How about the y-axis? Is that density? Yes, it's density. Okay, so that's a histogram. Type. Why do we have equal size bins here? Because that's what we defined, right? That's this array. It's 0, 10, 20, and so on. The other one where we manually put the numbers to be different. Okay, but here the step is constant, so we get something like that. So still this is a histogram, and it's just different bins. If we didn't give the bins, so you see here we gave the bins array, right? So we define the bins. Here, if we excluded the bins, by default, okay, the data science package, the method hist, will assume 10 bins of equal size based on the range of the values. So the range of the values, remember, is 3 to 99. Okay, so it will divide the range 3 to 99 into 10 equal bins, and we'll do the histogram based on that. So that will be the histogram if we excluded the bins. So the bins here are 10 bins equally sized from 3 to 99. Okay? Why these are different? Why are these two plots different? Are they the same or different first? They are different, right? They clearly different. Why? Do you have the same bins here? No, we don't have the same bins. Okay, this one starts from 0 to 10, 10 to 20. This one starts from 3 actually. We said that the bins from 3 to 99. So the definition, the bin sizes here is different, and that's why the count, the values are different. Okay, so let's get back to the slides. And this is a summary of the density issue. So we said that the histogram uses the scale if norm is equal to, okay, and that's the default. And that ensures that the area of the chart sums to 100. What does that mean? That means that the areas, the total areas of the bars is 100. Right? Why is that? Because we said that the area of each bar is the percentage, right? Percentage of all. If we sum all the percentages, of course it should sum to 100. That's the whole population. The horizontal axis is a number line, it's to scale, and the bin sizes don't have to be equal, and the vertical axis is a rate. It's a percent per unit or per year in our example. Here's how it's calculated. So the 40 to 65 bin in our example had 52 counts, 52 individuals, okay, out of 200 movies. So the percentage of the population in this bin is what? How do we calculate the percentage? 52 divided by 200, which is 26%, right? Now, is that the density? No, it's the density is that percentage divided by the width of the bin, right? So the width of the bin is from 40 to 65, so the width of the bin is 25 years. So to get the height of the bar, which is the density, we divide 26% by 25 years, which is 1.04% per year. And I hope it's clear from that calculation why we call it percent, why the unit here is percent per year. Because the unit here is percent, okay, and we divide it by number of years, so that gives us the unit to be percent per year. Okay. So that means that the height is the percentage of the bin over the width of the bin, and the height measures the percent of the data relative to the amount of space space in the bin, which we call it the density or crowdedness. Okay, crowdedness or density, and the units is percent per unit, as we just mentioned. Now the area, if you look at this equation, that means that this is the area, right? Because height times width is that, so the area is the percentage in the bin. Okay, so the area indicates the percentage or the count of the individuals, and the height is how crowded the bin is. Okay, any questions? So what remaining is to go through this, which is the same exactly like what we had just went through in the slides. It will calculate exactly how the densities are computed. Okay, we'll go through it quickly next time, inshallah. Do you have any questions? Is the concept of the histograms clear? Yes?
Can we define a bin with a range of minus infinity to 3, for example?
Can we get what?
Can we define a bin with a range of minus infinity to 3, for example?
Final bin?
Infinite.
Okay,
Can we define a bin with a range of minus infinity to 3, for example?
If minus infinity can be represented, then you can, but yes. But you don't need that if you know the range, right? And if you know where the data starts, what are the minimum value of your data, and what is the maximum, you don't need to have these extremes. But if minus infinity can be represented, or infinity can be represented, then yes. Generally it can, yes. Okay, that's a good point. Okay, okay. And now I see why you are asking this question. Yes. In this case, it won't. You cannot plot it, right? You cannot plot it. Yeah. So I don't think it can happen. Yes. Yeah. Good. But of course, you can try with a very long number, a very big number. Okay. But the graph. You will see that this bin will be very wide and the others will be very small. I don't know if that's what you want But if you want to play with it, yes, you can, of course. Yes. We cannot guess. You can try and see, okay? But in reality, probably you don't need that. As I said, if you get the minimum and the maximum values, you know the range, okay? So you plot what you want. One last point before you leave. I know that you want to leave eventually. The flexibility that we have from the histogram is really nice because you see here, we didn't zoom into this bin, right? But we can if we want. This is giving us the percentage over this bin. What if I want to zoom in and see what's the distribution within this bin? What should I do? I should make finer grained bins, smaller bins. So I can say bins from 40 to 45, 45 to 50, 50 to 50 to 55, and so on. And see the distribution for each, exactly as we did here. Right? You see here, we could have a bin from 0 to 15, right? But we defined these 3 bins because maybe we are more interested in this range. So when you have data, you can easily zoom in into the bin or the range that you are more interested in and see the distribution. Because here the distribution over this 25 or this 25 years, right? So the distribution, the exact distribution over the 25 years is hidden here, right? You don't see it. You just see the percentage of that bin. You don't see what is the distribution over the years within this bin. If you want to do that, then of course you have to define more fine-grained bins. Okay, see you next time, inshallah. Thank you.